The very foundation of circuit analysis comes from the laws of Kirchhoff's. So in this part of the module, we will discuss the concept of Kirchhoff's current and voltage laws and give some examples. Kirchhoff's laws are composed of two laws known as the Kirchhoff's current law or KCL and Kirchhoff's voltage law or KVL. These laws were introduced first by the German physicist Gustav Robert Kirchhoff way back in 1847. So what is Kirchhoff's current law? The law states that the algebraic sum of currents entering a node or a closed boundary is a zero. So to explain, let's say we have here a node and 5 currents either enters or leaves the node. So in this case, I sub 1, I sub 4, I sub 3 are entering the node, while I sub 2 and I sub 5 leaves the node. According to Kirchhoff's, if we assume that the current entering the node is a positive and current leaving the node is a negative, according to the law, the sum of all the currents that are entering minus the currents that are leaving the node is equal to 0. The same principle applies to a boundary. So let's say we have here a boundary, a closed boundary where it may consist of sub-networks inside. So let's say currents are also entering and leaving the node. So the same principles or principle apply to a closed boundary. So this law or the KCL is based on the law of conservation of mass. So take note that current is simply the flow of charges, and the principle is that when charges enters the node, those charges must leave the node so that there will be no accumulation of charges on the node or inside the boundary. KCL is useful when it comes to nodes where more than 2 currents is entering or leaving the node. So in this example, uh, let's say we take node A here. So this is node A, and we say that by KCL, all currents entering minus all currents leaving must be equals to 0. So in this case, we have at point A, we have this relationship for all the currents that enters and leaving the node A. And also point B, we can also formulate KCL on that node. So currents entering the node, so I4 minus currents leaving I5 and I6 must equal 0. If I take, for example, this boundary here, okay, and consider this to be a closed boundary, I can say that the currents entering and leaving this closed boundary must also equals to 0. So what are these currents? So take note that this is also I sub 4. This is I sub 2 here. This one is also there's current leaving here, which is I sub 1. So take note this is I sub 1 because it goes all the way here. And this current here is entering the boundary and also equals to I7. Here, this is I sub 6. So we can do a formulation there. We can write KCL there as currents entering. So we have I4 plus I7 minus the currents leaving. We have another one entering, and that is I sub 2 here, and minus the leaving. So I sub 1 and minus I sub 6 must also equals 0. Now let's go to Kirchhoff's voltage law. This law states that the algebraic sum of all voltages around a closed path or loop is a 0. To explain this law, let's say we have a closed path here. So we assume for the moment that we know the voltage across all the elements around the loop, and that we also know the polarity of those voltages. So according to KVL, the sum of those voltages, the algebraic sum, must equals 0, or for any elements, the summation of all the voltages across the elements must equals 0. This law is based on the law of conservation of energy. We will not derive why is that so. We simply state that the sum of all the voltages around the loop must equals 0. The one question perhaps is, what is the sign of the voltage when we added it algebraically and equate to 0? So for example, y v sub 1 is negative, v sub 4 negative, and the rest are positive. So to explain this, first let me label these nodes as A and B. And let's say starting from A, I go around the loop in a clockwise direction. And then so as I approach element 1, and when I entered element 1, I first encountered the negative sign there. So I put a negative sign for V1, for the voltage V1. And then I left element 1 and proceed to element 2. And the first sign I encounter when I enter element 2 is a positive sign here. So therefore, I write plus V2. Then afterwards, I proceed to element 3. I first encounter the positive sign here, so I also write plus V3. Same for V4. When I enter V4, I first encounter the negative sign, so therefore I put there negative V sub 4. And when I arrive at point B, I encountered the positive sign for element 5, so I write plus V5 and then equate that to 0. So that is how we determine the signs of the voltages across the elements. So this is the rule. So as we go around the closed path, we sum up all the voltages across each element with the sign of the voltage taken as the first sign encountered as we enter the elements. Uh, or we could also use the last sign encountered as we exit the element. So for example, instead of the sign I first encountered when entering the element, I use the sign when I left the elements. So for V1, that should be positive V1. For V2, that should be negative V2 because when I left V2, it is a negative sign. Then for V3, when I left V3, is a negative sign. For V4, it should be positive, and V5 minus V sub 5, and also equate that to 0. And you'll notice that this is just the same as the previous equation that I've written. It's just it is multiplied by -1. Now, there's another option when formulating uh, the equations using KVL, and that is if you want to go in the opposite direction. So let's say instead of clockwise direction, let's say I go from B to A in this direction. That is also possible, and you could also use in getting the sign. You can also use the either the first sign that you encountered or the last sign encountered as you leave or as you enter or leave the element. So let's have a very simple example to show how KVL works. So here I have a very simple circuit, and we're asked to determine the current I. Now this current can be determined simply using Ohm's law by getting the equivalent resistance, which in this case is 50 ohms, and we will get there 100 divided by 50, and you'll get there 2 amperes. But let's say we're going to use KVL here. So to use KVL, first we need to label the voltage across the elements like that. So for the source, we don't need to label it as the magnitude or the value, and its polarity is already indicated. And then the next is determining the sign of these voltages. Now, in determining the sign, the rule is that the side where the current enters the element, which is in this case is the resistor, that side should be the positive polarity. So in this case, we have here it should be positive here, it should be negative here. For 15 ohms, since the resistors are all in series, this is also I here. So therefore, this is also positive since the current enters on that side, and this is a negative. Also, this is I here, and therefore this should be a positive here, and this should be a negative. Okay, so V3 here should be positive, negative here. And then after doing that, we can now write the KVL equation. So summing up all the voltages. So let's say coming from this point here, then I go around in a clockwise direction. So I encounter the negative sign, so minus 100 plus V1, then plus V2 plus V3 equals 0. So that should be the how the equation should be written using KVL. Now to get I, take note that V sub 1 is the voltage across the 10 ohms, and that can be replaced by a current using Ohm's law. So we take note that V sub 1 is equals to 10 times I, V sub 2 is 15I, V3 is 25I. So replace that by that and transfer the negative 100 on the other side. So we get this one. And simplifying it, we get this one. And finally, we get the answer. So we get the same answer. It's just a bit longer, but this is a very simple example of how to use KVL. In the previous example, the use of KVL there was a sort of an overkill. So let's put to use KVL in a more complicated problem. So here we have a network with two independent sources. So we have the 5 volts and the 3 volts. And then The problem is asking us to find I sub 1, which is in the indicated direction, and also the voltage V sub 3 with the indicated polarity as well. So in this problem, we cannot use simply here a simplification of the circuit, uh, mainly uh, because of the presence of multiple or dual voltage sources here. We cannot also apply here Y to delta transformation because the result on that result we cannot also um, zero in on the solution, and therefore those tools that we have learned before are not that effective. So um, for this problem, the use of Kirchhoff's laws is more fitting. So let's proceed with the solution. So the first is we label the nodes where there are more than two elements connected. So here we have here node A and node B. Then we assign currents to all the elements. So here we assign for the 8 ohms, we assign I sub 2, and for 4 ohms, we assign I sub 3. Now the direction of the current is simply arbitrary, so we could have made I sub 2 in the upward direction or I sub 3 on the rightward direction. Now for 5 volts, we don't need to put a current there because the current here is also I sub 1 because 5 is in series with the 2 ohms. Likewise for 3 volts, the current here should be I sub 3. The next step is to label the voltages across the elements. So for the resistors, uh, for 2 ohms, we have here the voltage is by Ohm's law, we have 2I1 with the positive side on the right side because current I1 is entering on the right side. So therefore, it should be positive there, and on the other side is negative. And the magnitude is 2I1. And for the rest of the resistors, so for 8 ohms, the positive should be here because I sub 2 is entering on that side, and negative here. Here this should be positive because current I3 is entering on the right side of 4 ohms. And these are the magnitudes of the voltages using Ohm's law. So to solve the problem, we need to apply the KCL of Kirchhoff's and as well as the KVL of Kirchhoff's. Now for KCL, we need to find nodes where there are more than two elements connected. So that will be nodes A and B. Now for node A, so we formulate the KCL there. So we write current entering minus current leaving must equal 0. So let's write there equation 1. Now we could also write the KCL at node B, and that would result into something like this: I2 plus I1, because I1 is entering here, because this I1 here will go all the way here, and minus I3 equals 0 because I3 is also here, goes all the way there. And you will notice that this equation is also this one, and therefore this equation is redundant. So we don't need this equation anymore. And what this says is that we already exhausted KCL. and we need to proceed to KVL to um, uh, derive more equations. To formulate the equations for KVL, first we identify the loops where we're going to conduct our KVL. So let's say this is loop A here, and there is loop B. So these are the smaller loops that we first look at and write KVL there. So we don't immediately look out for larger loops. So let's say this loop here. So we don't do that. Uh, so again, this is A, B, and then we start in loop A. So let's say we start here and we move in a clockwise direction. So we first encountered the negative sign of 5 volts, so we write there negative, and then we proceed to the next element, 2 ohms. We encounter the negative sign, so we put here negative, and then we go to 8 ohms where we encounter the positive sign, so we put there positive. So we get this equation, and um, simplifying it, we get this one. So that would be our second equation. And for loop B, let's say we start here and we go also clockwise. Um, so we first encountered the negative sign of 3 volts. We put there negative. Then when we arrive at 8 ohms, we encounter the negative sign here. So we put there negative 8I2. Then for 4 ohms, negative 4I3. And then we simplify it and we get this third equation. So we bring the equations together, and we don't need any more additional KVL equations because the three equations that we have developed is already enough to solve the problem. And if we attempt to create another equation, let's say around this super loop here, that equation may be redundant. Okay, so we have these three equations, and solving the three equations will give us these currents. And therefore, given those currents through the elements, 2 ohms, 8 ohms, and 4 ohms, we can solve for V sub 3. Now, in solving V sub 3, notice that uh, the polarity of the voltage across 8 ohms based on the direction of I2 is that this is positive, this is negative. And since we're looking for V sub 3 with the opposite polarity where this is positive here and this is negative, we need to put a negative sign here before we uh, solve for 8I2, which is the voltage across the 8 ohms. So that will give us a negative 2 voltage. In this example, we have here two sources, and one source is an independent source and the other one is a dependent source. So the dependent source is dependent on the voltage across the 15 ohms with a given polarity. So the problem asks us to determine what is I and the voltage V sub A. So we cannot use KCL here because this is only one loop, and the nodes here are very simple nodes where only two elements are connected. So let's say this node here, there are only two nodes, two elements here, here, and even here. So KCL won't do much here for a single loop. So what we can use here is the KVL. So to use the KVL, first we need to label the voltages across the elements that whose voltage are not yet identified. For the 30 ohms, the voltage there is 30I by Ohm's law, and the plus is on the left side because I is flowing towards that side. For 15 ohms, well, we already have a label for the voltage, so we can use that in our KVL. So writing the KVL equations, so starting here, so that would be negative 120 plus 30I plus 2VA. So the magnitude of this voltage is 2VA minus, because there's a minus sign here, vis-a-vis equals 0. And we can simplify that and tag that as our equation 1. So we have here two variables, one equation, and we need one more equation, and that will come here because the voltage across the 15 ohms in terms of I is also 15I, where the plus sign is on top and the negative is below. And since the problem also labeled this voltage as B sub A, only that the polarity is in the opposite, we can say that 15I should be the negative of B sub A, and therefore we can form another equation out of that, and that would be our equation 2. So solving the two equations, that should give us I here and B sub A. Now for our last example, we have here three sources, three independent sources, two voltage sources, and one current source. So we are only asked to form the KCL and the KVL equations for this circuit. So to solve this, first let's label the loops, the small loops as A and B and C, and also the nodes bearing three or more elements. So this is loop nodes 1, 2, and 3. The next is we assign arbitrary currents, so any direction will do. So we have here I1 through I1 ohm, and I2 for 2 ohms, I4 for 8 ohms, I3 for 4 ohms. So 20 volts. This is also I4 here. For 40 volts, this is also I1 here. Now we don't need to label current here on the current source because the presence of 5 amperes here means that the current here is already given, and that is 5 amperes. So that current flows from here until here. So all the way to node 2 from node 1, and that is 5 amperes. So there's no need to label that part of the circuit, label the current. Then we assign voltages across the resistors. So here this is 1I1, here this is 2I2, 8I4, here is 4I3, and the polarity is assigned based on the direction of the currents that we have assigned. Okay, so first let's form the equations based on KCL. So from node 1, so we have three elements connected there, we can form a KCL equation there. So current entering is I1 and I2, minus I5. So I5 is, or 5 amperes is leaving here. So I1 plus I2 minus 5, or we transfer that to the other side of the equation, that will become equals 5. Then for node 2, you can also formulate the equation. So current en current entering is I3. I3 is entering, so we have it positive there. I2 is leaving, so we have it negative I2 there, and I4 is also leaving, so negative. Also, 5 amperes is entering node 2, so therefore it has to be plus 5. And then we transfer that on the other side of the equation, that becomes negative 5. So that is our equation 2. Now we could also produce one equation for KCL on node 3, but it is possible that it is redundant. So we leave KCL and proceed to KVL. Okay, so for loop A, we add all the voltages. So let's say we start here. We start here and go clockwise in this direction. So that will be positive I1. Then for 2 ohms, that will be negative 2I2. Sorry, this should be I2 here. And then for 4 ohms, that will be negative 4I3. So here, and then minus 40 once we go there to 40 volts. So minus 40 volts, or we transfer that again to the other side of the equation. So we'll get this equation. And for loop uh, C, so this should be loop C here. So again, we go around clockwise, starting here. Okay, so first we encounter the positive sign of 4I3, so this is plus here, plus 4I3. Then next we go to 8 ohms, we encounter the plus sign there, so we have 8I4, and then we encounter the negative sign of 20 volts, so minus 20, and then we transfer it on the other side, and we get here 20. This is 20 supposed to be. Now, so we have 4 equations all in all, and that should be enough to solve the problem. Now, why didn't we write KVL equation for this loop, loop B? Now, we can do it, but that would require us to know what is the voltage across these 5 amperes. However, since we do not know that voltage, take note that this is not a resistance that we can multiply with a current. This is simply a current source. So we don't know that voltage there initially. So there's nothing that we can put in the equation to form the KVL equation. So loops that contains current loops, we initially avoid them, and we only look for loops where there are no current sources, and we write those equations. So these are the equations. So we have equation 1, 2, 3, and 4. And that should be enough to solve all of the currents, the 4 variables. And once we get those currents, we can solve the voltages. So for example, V naught can be solved using this. So again, V naught is opposite in polarity compared to the polarity of 4I3 here. So we should put a negative sign there, before we solve for I3. So that's it for our introduction to Kirchhoff's laws. So as mentioned in the beginning of this video, Kirchhoff's laws are very basic uh, tools in the analysis of circuits, and it can become long in terms of solving the problem if we have a complicated network. Now, there are techniques that shorten the way the circuits are solved, and that would be discussed in our next video on mesh and nodal analysis. So I'll see you in the next video.